I'm going to walk you through a more complicated example of recursively defined program that processes a piece of data according to its syntax. So it's from chapter 1. So here's my repository. I'm going to chapter 1. It's called the substitution program. So we're creating a procedure that can substitute a new symbol for an old one in an S list. Okay, so here example, this is S list. It looks like a scheme list, but it's a list of symbols and other lists. Then you see after B is replaced by A, we're gonna get this, right? So this is a test case. So now to write this program, we're gonna follow the definition of S list because it's recursively defined. The shape of our procedure should match the shape of the data because that's the easiest way to think about it. So what is a S list? An empty list is by definition a S list, or it can be a S expression followed by a S list in this in this const pair. So this is really what this means is we can have a list and whose element is a S expression, but this S expression can be one of the two things. So it can be a list itself, so this is recursively defined, and then but it can be a symbol, like simple as a simple item as a symbol, or it can be any S list, which is recursively defined here. So now this is we have two non-terminals on the left hand side, right? Two syntactic categories. So that it's more complex, but this is it has to be this way to define this kind of structure. So yeah, so a S list is really something like this, right? It's a list, and each element can be a symbol, or it can be a list, S list, which is defined in a similar way. So this is one way to do it. So note that this is a dotted notation, so that means this is a const pair. But this is exactly how we what happens, what we get if we prepend something to a list, right? So we have the list, the original list as the remainder of list, and then in the const pair as the curter part of the const pair, and then the car part is this new thing which can be a symbol or can be S list. Okay, now to define this we need to define the procedure, and then we follow the grammar really strictly. So if the S list is empty, it's an empty list, then the result is empty list. Okay, straightforward. Otherwise, depends on what it is. So otherwise it can be this, right? It can be so it's consists of two parts, an X expression and then a smaller version of the S list, right? Concatenated together or in a const pair. So that's what we're doing here. We use const pair. We create a const pair, and the first part is gonna be this S expression after the substitution is done, right? So we need another procedure to do this, a helper procedure, we call that, and then we pass in the symbols, and then we pass in the car of the S list. Okay, and then the curter part should be the remainder of the list with the old replaced by the new, or the new substituted for old, right? So that's the recursive part. And then let's look at the helper method. In the helper method, we know the parameter, the third parameter, can be one of the two things, symbol or S list, right? If the input, okay, we assume the input is grammatically correct, right? If it's correct, it has to be one of these two cases. So we use if to tell them apart, right? If the expression matches the old, which means well, if it's a symbol, right, first, and then it matches the so then depends on whether it matches the old or not, we return a new symbol or just the old symbol, the symbol as is, right? So this is when it's a symbol. But if it's not a symbol, we're back to the same problem, right? If it's not a symbol, it has to be a as list according to the grammar. Now how do we substitute a new for old in this sublist, in this as list? Well, we have a procedure that does exactly that, right? So we can call that procedure to get the job done. So we're going to run a test in a moment, but you can see these two procedures work together. They're mutually they're mutually recursive, right? So subst is defined in terms of the helper and itself. And the helper is defined in terms of this procedure, right? So they're mutually recursive. And then this is a very important technique for writing this kind of program because this allows us to divide and conquer, right? We decompose this into two procedures so that we can think more clearly about this complicated problem we're trying to solve. We're following the grammar. This is very helpful. And then so it's imagine if you had to write this in one procedure, it would be much more complex. Okay, so I can copy the code. I already have it here. I can test it with a test case, and I can trace it to see the inner working of those procedures, the process generated by those procedures. Okay, so I'm going to run this, and the answer is expected. If I comment out the trace, I can do some tracing. Okay, so now it's quite long because it's complicated. So now let's start with the first call. We're gonna call this is the initial call, right? So since the car of the sublist, the S list is okay, we're gonna treat it as expression, right? We call this helper, and then in the helper we found out this is actually a S list. It's not a symbol, so we turn around, call substitution procedure to get the job done, right? So then the car of this S list is a symbol, so we call actually we're gonna call this to deal with the car the first part of the pair, and then it returns A because B needs to be replaced by A. Then the remainder is a S list, right? It's the remainder of this is S list, so we call substitution method, and then we call it a helper, and then it's gonna replace B with A in C, and then the result is just C, and then there's a remainder of the list which is empty, and give empty. On the way back we cons, right? We rebuild the list, so C turn into C because B doesn't occur in this list, right? So once that is done, we gonna way back to return from this, which will give us AC, because AC is BC with the B replaced by A. So that is done. The car part is processed, but then we're gonna process the coder part, the input. Then I'm not gonna look into that, but this is as you can, because it's mutually recursive, so you see the different method. One uses another, but in the end we get let's see, we get A, empty list, and D, which is this one with B replaced by A, right? And then finally the first call can return. We're gonna put the two together, so AC becomes the first part of the car, and then the remainder of the list. So we just append the two together, so that it gives us the final S list. Okay, so yeah, so this is a more complex problem, so take your time, read the descriptions, and maybe start with a simpler case and trace it, and so you can develop some intuitive understanding of how this procedure or how this algorithm works. Okay, that's it.